All right, welcome to Module 5. We're looking at some more maintenance management techniques. In particular, we're going to be looking at a lot of mathematical modeling, and in what we term that as being is quantitative techniques. Qualitative techniques are, say using somebody's experience, and they talk about, oh well, generally it's this kind of size, and normally it takes this long to do that. So it's all about quality, not quantity. So quantitative analysis or quantitative techniques, they use numbers. So a lot of the mathematical modeling that we'll be doing, of course, we'll be using probability theory. And that will range from normal distributions, Poisson distribution for argument's sake, binomial distributions. And you would have covered a lot of that in your first year mathematics. Also statistics is used, but even so, Appendix 2, if you go back over that, you'll see that there's a whole range of mathematical concepts that might be able to help you come to terms again with some of that terminology and also some of those practices. So modeling, whether it's the equipment life plans or the maintenance strategy, what we go about doing is solving maintenance problems through the consideration of the reliability of machinery. Now, again, it relies on the reliability of humans as well and organizations, but from a maintenance technique, we'll be looking at the reliability of the machine itself and how it fits into the system and its criticality in that regard. Is if it goes down, does the whole process stop? Is it such a critical part of the whole process that the whole production line falls over? The mathematical models are used primarily, they come from a scientific approach, a mathematical approach, and they're going to help with maintenance management decisions, whether it's scheduling or maintenance planning, and also in terms of workforce planning for your maintenance unit. And basically, obviously, you might imagine, it's a mathematical model, so it represents the actual system or the organization that you're involved with, or the processes that are involved with decision making for maintenance processes. Now, life plans relate to fundamental decisions on how assets should be maintained, and what, how, when, and who, basically. So when you look at your maintenance strategy or your maintenance issues or maintenance opportunities, what is it? What should be maintained? So you go about identifying what's causing you to define the maintenance processes or the maintenance strategy. How should it be maintained? Is there an OEM? Is it under warranty? Is it an old piece of equipment? Is it going to run to fail? Have you budgeted to replace it? Have you got condition monitoring, checking it all the time? Are you patching it up all the time so it's always under repair? And you always know, oh yeah, pump number 3, that's always a problem, blah, blah, blah. Just, it'll be that, you'll have a real feel for that particular problem. Or, do you have to go back replacing this thing? When should you maintain it? So there's a whole range of, whether it's a warranty issue, whether it's, a maintenance strategy for a particular device, a haul truck or whatever, an air filter in a bulldozer, whatever the case may be, there will be, set down time limits that should be changed, every 10,000 hours or something like that. So that might be already specified for a particular item, but then again, a whole haul truck, what do you do with it? Whether it's the oil filter, the air filter, is it something to do with, the tires? So yeah, what's the maintenance schedule? When are you going to do it? And who should do it? Obviously, you've got a range of tradespeople. Are you going to get an external contractor coming in and doing it? So therefore, how are you going to go about scheduling the resources and commitment that you need to get this thing maintained. Modeling, failure and plant replacement, primarily associated with the when or the timing aspect of our maintenance. And so when we look at these mathematical models, it'll be about looking at, is the device, the piece of equipment, is it going to fail? When's it going to fail? How often will it fail? Or is it about the replacement of it? So basically all that modeling will focus on that. So what are the benefits for mathematical modeling and when we're considering the failure or the plant replacement? We must consider the impact of selecting the wrong frequency of maintenance actions. You know, so sometimes we find that you can over-maintain as well as under-maintain. In the absence of failure modelling methods, you require an estimate of the best timing of the maintenance action. So, best estimate, where's that come from? Yeah, and that's what we're talking about. Yes, I've got years of experience, and yes, I reckon it should always be done on a 10,000 hour changeover. Well, maybe not. Maybe that's under maintenance because of the conditions currently in your mine frame. They might be very dusty, so your air filters may need to be changed more often than that. It just depends. So the mathematical model is going to bring out a far more quantitative way of being able to help you estimate far more better predictions. So it's possible to provide an informed or accurate estimate to schedule your maintenance. But without sound knowledge of the fail patterns, your cost of planning, unplanned failure, such estimates can vary widely from the optimum time to schedule maintenance, and oft-times estimates based on calendar intervals, weeks, months, or years. In other words, we're going to change that over every 6 months. Yeah, look, you can do that, but they really have no factual basis. It's basically an arbitrary time setting. So it results in great deviations from the optimum times to undertake maintenance. You may not need to, you may have to do it every 3 months, not 6 months. So the error in timing of your maintenance frequencies, as I say, if you do it too frequently, you're over-maintaining. If you don't do it frequently enough, well, it's under-maintained, and you're going to have more stoppages, breakdowns, that type of thing. So the consequences of over-maintaining, well, there's an increase in preventative maintenance effort because you're forever maintaining this thing, and how often is it actually operating? The labour and material costs associated with the inspection or repair and replacement, well, potentially there's multiple times of higher than necessary. So if you keep checking on this thing, it costs money for it to be pulled out of action and where it should be doing stuff rather than being maintained. Downtime associated with the preventative maintenance is higher, resulting in greater losses and opportunity costs. So, by the way, opportunity costs, they represent the benefits that an individual or a business misses out on when choosing one alternative over another. So just give you an example. You might hear that terminology, opportunity costs, thrown around all the time. So basically, it's the difference between the expected returns of whatever options that you're looking at. So opportunity cost equals the return of the most lucrative option not chosen, minus the return of the chosen option. So just to give you an example, if you've got, you're looking at your budgeting for argument's sake, and you were able to go and invest that in the stock market, and obviously that's a way to generate returns, and let's say you can get a 12% return. The second thing might be to go about reinvest your money back into the business, expecting to buy new equipment, and that'll increase your production efficiencies because you've got brand new equipment, nice and shiny. It's not breaking down. So that will lead to obviously lower operational expenses and a higher profit margin. Let's just say, by your calculation, it's going to give you 10%. So the opportunity cost of choosing that equipment, so let's say you chose the equipment over investing money in the stock market because, well, that's quite bubbly at times. So 12% minus 10% is 2%. So opportunity cost, as we say, is the return of the most lucrative option not chosen, minus the return of the chosen option. So 2% opportunity cost in that particular case. You've lost 2% by choosing to go and buy the new equipment over investing in the stock market. Consequences of under maintaining a particular piece of equipment, it's reduced preventative maintenance effort, higher incidence of unplanned failure, safety or environmental consequences associated with the unplanned failures, labour and material costs associated with the unplanned maintenance, potentially higher than the planned maintenance because obviously, again, you might have to do far more maintenance than you would normally do. Downtime associated with the unplanned maintenance, potentially higher with greater losses and obviously opportunity costs. Failure and replacement modelling facilitates the optimisation of maintenance action to avoid over or under maintaining and the associated penalties and consequences. All right, so as we say, you can over or under maintain things. Typically with these models, we say we're going to focus on modelling failure or modelling the replacement. So failure of items and their associated systems exhibit certain time-based characteristics. And again, you've got to have data to be able to figure out what these time-based characteristics are. For example, it's unusual for multiple identical light bulbs to fail at exactly the same time. All right. Now, if it wasn't unusual, then you could plan for maintenance straight away before it even failed, because you know that all of those things are going to fail. Well, welcome to the real world. It doesn't work like that, does it? So in reality, numerous factors influence the relative life of a particular item, even identical items in the same location, whether they're light bulbs, spark plugs, air filters, oil filters, tires, whatever the case may be. So there are minor variations in any number of factors that can impact on a specific and individual item's observed life. The installation of it, how about you go putting it in, if you installed it correctly? Have you installed it so that it's defective right from the start because in installing it you've broken part of it or something? The materials themselves, the handling of those materials, and of course the use that they're put to. So all of those things, those little minor variations, whether you're putting in 3 air filters in 3 different vehicles or whatever the case may be, there might be slight different things that are going to cause, obviously, their failure to occur at different times. And of course, the manufacturing of those things, sometimes they're just faulty, manufacturing. As the item failures occur, patterns emerge that, obviously affect their decisions on which is the most appropriate choice and timing of your maintenance actions. But the key thing, of course, is that you've got to have data. So to model these things, you've got to start collecting, information. Sometimes the manufacturer can tell you straight away, again, that this has a 10,000 hour life, that type of thing. So, but the key thing is that obviously the organisation that's produced that air filter, oil filter, has obviously collected data over time. So multiple failures of identical items can be analysed to provide a probably failed distribution of time. So whether it's the manufacturer telling you that or you and your organisation, that will help you with your maintenance planning. All right, so modelling failure, we can look at the mean, the variance, and standard deviation. So let's have a little example. Consider the failure data for 100 items over 6 months. So this table 5.1, we've got 6 failures of whatever this item is. In month 1, in the second month, we have 12 failures, third month, 30 failures, fourth month, 25, etc. So we can calculate that as a percentage, and we can calculate it as a relative failure frequency. So when we do that, what that means is the relative failure frequency is the number of fails in a month divided by the total number of failures that you have. And then you can accumulate those percentages and ultimately draw a cumulative graph. All right, the other thing is you can draw a histogram. Let's look at the histogram. And again, you can have the mean of the failed intervals by simply taking halfway between each of those intervals. So the histogram is what we call the failure probability distribution for that particular item working under the test conditions. And it's reasonable to predict failure of identical items in similar working conditions based on that historical data. So again, it's important to collect that data. And again, it's going to help you figure out when you need to either, replace something before it fails, is the key thing, of course. You don't want to keep replacing things once they fail because, again, that's not very strategic maintenance. All right, now the mean, variance, and standard deviation, you can actually do that as calculations, of course, and something we would have covered in first year maths. So if we go about for that particular data that we have in that table, we're able to go about calculating the mean. So when we do that, as you can see, the study guide will do some examples, and you'll find that I will take those and give you far more detail. So when you see that difference between that, that's what I'm doing in these lecture slides, is bringing out more details to give you better strategies and insights to how the calculations were done in the study guide. So a little formula that we use in this case, it's based on the frequency. So therefore, capital M, the mean, is equal to the summing up of all of those little frequencies multiplied by those little averages in that particular interval. So over this particular 6-month period, we've got little frequencies from the table of data above. And we've got our little means of the failed interval from our histogram as well. So by combining those two things, we can go about calculating the mean for the failure. So basically, 4.76 months is the mean that we're finding here for things that are failing overall for each of those individual items. Then you can calculate the variance, and again, this is variance is pretty much how far something differs from the mean value. So if the average, as we saw beforehand, was 4.76 months, some things obviously will fail before that, some things will fail after that. So the variance is a calculation of how far beyond, below or above the mean. And again, we can do, there's a little formula, general formula. So we're talking about 6 months, of course, overall. So again, when we calculate that, the variance is 4.354 months squared. We can go from that and find the standard deviation, which basically is just the square root of the variance. And again, the standard deviation is a statistical measure of how tightly bunched things are around the mean for various data points. So yes, so again, these are mathematical measures, basic measurements, very simple, straightforward, statistical measurements to give us some insights into predicting what's going to occur so that we can basically replace things before they fail. There's a whole range of different probability densities. We can have this type of one here. This is a normal distribution fail probability. We can go about analyzing that, and as you might imagine, since we're fiddling things to models, to fit it to the model, the mathematical model already has a range of characteristics. So for a normal distribution, as you see here, if the times to fail is distributed, as per a bell-shaped curve, or that normal probability density, or just normal curve basically, then we can see that 50% of the fails will fall in the range between 0.65 standard deviations either side of the mean. That's that shading you can see there. And also the 95% of failures fall in the range from 2 standard deviations. And again, you can look up standard deviation tables to help you do calculations. And again, you've done this type of thing in your first year mathematics. Statistical tables give other percentage probabilities for other ranges expressed as multiples of your standard deviation, like within 3 standard deviations, within 5 standard deviations, that type of thing. Now, with some failure data, the mean and the standard deviation values could be calculated in a failure distribution estimated using this normal probability distribution function. As I say, there are others, binomial, Poisson, that type of thing. The probabilities of failure at various replacement times could be estimated at an optimum replacement time selected based on the cost of planned versus unplanned replacement. So again, we're able to read off and say, well, okay, then I have to do this within this particular time, 6 months, 2 months, what the case may be. Now, normal probability density function is useful for modeling failures where a distinct wear-out pattern is evident. So again, the mathematical model fits the particular maintenance problem. That's the whole point of it, isn't it? It's no good having a mathematical model that doesn't fit your particular problem. But for particularly wear-out patterns, the normal probability distribution works quite well. In reality, failed distributions do not follow normal distribution, and other distribution functions are considered more appropriate in those particular cases. So as I say, for that particular situation, the wear-out pattern fits really nicely to a normal curve, but other situations, flat tires, changing oil may fit better, if you're talking about scheduling, for argument's sake. If you're talking about your maintenance scheduling, queuing or Poisson distributions would fit that much better. So you can end up, again, a negative exponential probability distribution function. Looks like this, so you get this exponential decay occurring, and then you can go about using that to find the mean time to failure. So it's just another model. And you can get hyper exponential probability distribution. So again, you're getting a lot very quick failing or situation occurring. So you get that exponential decay occurring. All right, failure probability. Here we're given an area under the probability density curve. You can use areas, read off times. Reliability function. We go back up here first of all. And this here, what we're seeing here is that you can plot out the failures over time, or the probability function for that particular failure. And as you can see, it's increasing from 0 approaching a failure of 1. If you remember in probability theory, you talk about a failure is if we set the probability of something to be, P, and then for it to occur, we say that the probability of something occurring is 1, or it could be 50% of the time, so that would be 0.5, or 75% of the time, 0.75. But then, of course, the failure, we talk about zeros and ones, that type of thing. So the function, the complete failure through to operating correctly is the way that we go about calculating that the range of 0 to 1 values. Probabilities only range from 0 to 1. So a number of measures can be derived from this particular curve, the reliability function that we'll look on the next page, and also age-specific fail rate information, or the hazard rate. So if we go about looking at the probability that an item has not failed at any particular time t, then we can calculate what's called the reliability function. And that really, if we take that function above and we take it, so 1 minus that function, that will give the reliability. So now this, as you can see, increases from 1 all down to 0. And that's form, that reliability function 1 minus f of t, the fail rate. If we use that form for relatively small time periods, it will model that quite well. For larger time periods, we'll see that it's actually an exponential function, and we'll talk more about that a little bit further down, and the way that we use that exponential function a little bit further down. The other information we can get is what's called age-specific fail rate or hazard rate, and that's defined as the fraction of those items that have survived up to a particular time t that are expected to fail per unit time. Also referred as the hazard rate or instantaneous fail rate. And it's the probability an item will fail given that it has survived for a particular time. So if we've had it for, again, 5,000 hours, then it's the probability that it will last 7,000 hours, whatever the case may be. So the hazard rate gives the most distinct pattern of failure characteristics. So again, as we cycle through, these are the kind of techniques that you would use to, for a project, your assessment, that type of stuff, and looking at how you would calculate those kind of probabilities. Very typical modeling failure curve. It's called the bar tube curve, and it looks like a bath basically. And what you're looking at is that looking at the hazard rate in the early life of failure, the random failures, and the wear-out failures. Of course, if you keep anything long enough, it's going to wear out. So they're the particular stages. You first instigate and put in, as I say, an air filter for argument's sake. Then there's some, as the filter's being used, of course, clogs up, so there's some early life failure. Random failure occurs where, whether it's an air filter or anything else, just randomness occurs. You get dirty fuel, it's very dusty, so with air filter again, or a fuel filter or diesel filter. It just depends on random failure because you've had dirty fuel going through it or you've had very dusty conditions. And then, as I say, as time goes on and on, it will just literally wear out. So that's the kind of pattern that you see that occurs. So let's look at those characteristics a little bit more. The early life failure, it's patterns are reducing hazard rate with time, indicates an item that's less likely to suffer a failure as its running time increases. This type of failure characteristic is typical of items that exhibit early life failures due to poor design, manufacture, or installation. The failure characteristic is created by early removal of the item from the statistical population. In other words, it basically falls apart and doesn't become, long into that statistical population. It doesn't last long. The concept of burning in items to get them through this early life or infant mortality phase is often used, particularly in the case of electronic items. Random failure, as we go through our curve, the random failure pattern, the age of specific failure rate is constant with time, as you see on the curve, over that time period, straight line. This section of the bathtub curve is often referred to as useful life failures. The term random failure is considered misleading as it implies there's no pattern to the failures rather than implying the case of a uniform failure rate. So yes, in other words, it is predictable. The wear-out failure pattern shows an increasing age-specific fail rate, in other words, age-specific in terms of the older it's there, with times it indicates an item that is more likely to suffer failure as running time increases. So keep using it, obviously, as I say, it gets older and older and gets worn out. This failure characteristic is typical for components that are subject to the ravages of time. Failure modes such as wear, fatigue, erosion, and corrosion typically result in a component exhibiting wear-out failures, although caution is advised in making assumptions in general. So again, you might say that things have been there for quite some time. It's just lucky that it's still there. But ultimately, it will wear out. So again, looking at that kind of data that we saw beforehand for that 100 items, we can go about starting to analyze this data for not just fail rates, but also for reliability. And you can do that little calculation as you saw, and also for age-specific fail rate, you can do a little calculation. So if you do that calculation by doing these, following that little formula, you'll find that you should get these values, and these values here for both the age-specific fail rate and also for the reliability. So if we plot that out, you end up with this interesting curve. But as you can see, that's over that 5-month period, 6-month period, it shows a trend of increasing hazard rate with time, hence a wear-out failure pattern that could be modeled using, say, a normal distribution, probability distribution. So again, you know, a manufacturer might give you this kind of information for a particular filter, piece of equipment, etc., etc. So you're able to start looking at that and start gives you a good starting point to start doing your maintenance planning and your maintenance scheduling. The modelling failure, application of the age-specific fail rate to the maintenance strategy. So what about this age-specific particular value? How does that help? Well, that bathtub curve is widely recognised, the demonstration of 3 types of age-specific failure rates or characteristics. So you get that early life, random failure, and that wear-out failure that we were talking about beforehand from that bathtub curve. The failure characteristics determine which categories of maintenance activities are appropriate for particular items. So there are 4 available maintenance strategies. You can get design out maintenance. In other words, we can reduce the problem by avoiding it. Condition-based maintenance, so you have condition monitoring of some sort. So you're monitoring the condition that the particular element or device is at. The fixed time replacement, so you just don't say, well, every 6 months, every 10,000 hours, or the operate to fail, so it's a run to fail. So each type of action not appropriate for all fail characteristics exhibited by the components, and the appropriate strategies for various failure characteristics are shown in this figure. So again, what we can do is map that on top of the bathtub curve, and that gives us an idea of the types of things that occur, as we say, for early life failure. We can look at some of our maintenance strategies. So in that case, the design out maintenance strategy works quite well. Whereas for something like the wear out failure, well, as you might imagine, once it gets to that age, you just run it to fail or operate to fail. There may be a fixed time replacement, so therefore then you just run that component out, that filter out for 10,000 hours, and that's it. And as soon as you get 10,000 hours, you throw it away. So this is mapping and saying to you, okay, you can fit those strategies to those age-specific fail rates. So what kind of maintenance strategies? Let's look at them a bit more clearly now. So the design out maintenance, it's appropriate strategy for all fail characteristics. So it doesn't really matter if it's a random fail or whatever. If you can design it out, well, then you're not going to have that as a failure problem, nor as a maintenance problem. So the only option apart from operate to fail, or in case of reducing those hazard or early life failure characteristics, is to redesign the aims. So the redesign aims to identify your problem, leading to the early life failure and rectifying them. Causes or the cases of random and wear out failure characteristics, redesign is again it aimed at improving the safety, reliability, or maintainability of the equipment and the components. So what you're trying to do is, cut the problems out before they even begin. Condition-based maintenance, well, the appropriate strategy for uniform hazard rate, the random failure, and increasing hazard rate, that wear out failure characteristics in that bathtub curve. And the aim is to identify an effective inspection task that will identify the failure mode or its symptoms. Now, it's not appropriate for early life failures due to the high probability of failure prior to the first task being performed. All right, so again, that's why when you look at that curve, it's been shown from studies that these are the best maintenance strategies for these particular type of age-specific fail conditions or situations. The fixed time replacement is an only appropriate strategy for increasing the hazard rate at the wear out failure characteristic. It aims to select an optimum replacement or overhaul interval for a component that is most cost effective. So in other words, as I say, if you know your air filters and your working conditions for your specific site, for argument's sake, it's every 10,000 hours, fantastic. So therefore then you can schedule to that. Other sites you might say, as you move from one industry to another, you'll know that, oh, hang on a minute, since this site is dustier, it's a different material compared to, say, if you're working in iron ore compared to working in coal, as you shift one industry to another. So you might say, oh, that's all well and good, but for this haul truck, this air filter, we've got far dustier conditions on this particular site, so therefore then it only runs to 8,000 hours. So again, you you lock into those fixed time replacements. It requires an understanding of the certain fail parameters, including the mean time to fail and fail versus replacement costs. So again, as I say, that either will come from your experience on that particular site and the data that's been collected on that site compared to, as I say, if you ship to another industry or to a different site, you would have those different information related to that. Now, the fixed time replacement is not an appropriate strategy for random fail characteristics, because if you've got a random thing and you've got this fixed time and random processes, by definition, then that failure characteristic will just happen, because it's random to some sort of probability failure rate. And there's no value in replacing or overhauling components in this category, as nothing has been gained. If you've got a random problem, random failure occurring. The probability of failure is equally high after the maintenance as it was before, because it's obviously random. The maintenance programs traditionally relied heavily on this fixed time replacement and overhauls. But over time, again, as I say, there was either under maintenance or over maintenance occurring, so better strategies were considered and put in place. The fixed time replacement strategy is only applicable in limited circumstances. It can be difficult to justify unless failure costs are significantly higher than replacement costs. All right, so in other words, if fixed time, if you're trying to justify and say, oh no, that can run to 10,000, well, the point of the matter is that suddenly that creates other problems, remember. So the replacement of not just the filter, but other things can cause major blowouts in your budget. So modeling failure, the statistical analysis using the Weibull analysis, and again, this is one technique. This analysis is typically used for statistical assessment of failure characteristics. It involves determining certain parameters from a historical failure data. And that's why you have to accumulate this data and keep track of it. For specific items and also for specific equipment, whether it be a haul truck and an air filter, and therefore then this is the kind of mathematical distribution that you get. That curve ft equals beta divided by netta, that expression there. So again, looks very complicated, but you can model that. And again, manufacturers sometimes model these things and give you a chart, and you just look up the chart or you look up a graph. And all the mathematics is already done in the chart for you. But again, sometimes you have to do it from your own mathematical analysis. So that will give you your distribution for the different characteristics of that bathtub curve. And the distribution approximates probability failure distribution for a given set of failed data. So in other words, if you have a lot more failed data, then again, this is going to give you better approximations or better predictions, estimates of fail rates. The fail probability function is given by that, and then the age specific is given by that. So that's that FT and ZT curve definition that came above. So for that particular distribution, we were able to calculate those using those expressions. So you end up with curves that look like this. So therefore, as I said beforehand, a manufacturer might have already done this for you. So even these are the mathematical equations. So when you get your, your particular item and you're looking at the manual, they might have little curves like this that you just basically look up. So you don't go and calculate them, they've already been done for you. So you're able to go and look at that and read off the graph when the best time would be to replace that particular item to avoid the whole hazard rate. All right, let's have a look at an example. A mining haul truck shown in figure 513 is powered by a turbocharged diesel engine. Failure data is kept on the supercharged failures of 3 of these particular trucks, and the supercharger running hours at failure are recorded. That's why you have to keep all this data. There have been 7 supercharger failures. The running hours of superchargers removed for these reasons other than failure are also important, as they have survived until this time. So it's not just failed things, but also things that haven't failed, because then obviously you can look at different rates of failure and start to analyze why. Why is that particular truck supercharger failing compared to that one over there? Now, it could be from, you might have different types of vehicle. You could have a Caterpillar vehicle haul truck compared to a MAN haul truck, for argument's sake, or a different brand, or it could still be Caterpillar or Caterpillar gear, but it could be different haul trucks, different size haul trucks or different models of the same haul truck. So, it's not just fail rates, it's also success rates. Why is that one running better? So these data are referred to as suspensions rather than failures, and the running hours of the superchargers still on the truck are also regarded as suspension data. This information on the 7 failures and suspensions is summarised in the table below. We'll have a look at that in a minute. This failure and suspension data and the suspension data from the superchargers currently on the 3 trucks is shown in table 5.4. So again, you collect all this data, you're able to start analysing it, and there's other data. So the failure and suspension data of table 5.4 is used to calculate an estimated probability of failure using the equations derived from the continuous failure function information above. The results of the calculations are here. So you go back to your calculation. So again, as I say, either you do these calculations or a manufacturer has done it. But in this case here, we're starting to analyse, obviously what's happening on site. Sometimes the manufacturer might give you some examples so that you can help you with your maintenance strategy. So as you do those calculations, you'll find that you're able to draw up a little graph. And as you draw up this little graph, you're able to plot it out. So if we start here with the blue line, the estimated failure probability is plotted against the fail time on this Weibull graph paper, and the line of best fit's drawn between the points. So here's all your points, your data points that you've been collecting. Okay, you draw through your blue line. Then a perpendicular line through the estimation point that you've used to estimate your shape. That'll give you some information with regards to that. So perpendicular through here, this red line. And then whether your beta value, so we've been able to estimate a beta value as you draw that perpendicular line, it turns out to be about 2. So therefore, if your beta value is less than 1, it means your hazard function is decreasing. Equals 1, it's uniform, and obviously increasing for beta greater than 1. And then also you're able to, as you can see, drop your line down to gather your estimate of the mean value for the time before failure. Although the calculations in the graph on these techniques are quite straightforward, the statistical reasoning underlying this is sophisticated. So here's some reading. We'll go back and look at the background theory. So again, just by some very simple calculations and keeping data on site, for argument's sake, you can go about starting looking at analysing, looking at the probability of the failure using this Weibull analysis, and of course the graphs to drop out and sort of see, you can calculate averages and overall figure out information that will help you with your scheduling and your planning. All right, another method is the fail mode effect and criticality analysis. This method is used for analysing potential system failures. It originally was conceived as a fail mode and effect analysis, FMEA, process for predicting failure in equipment, design, and mitigating failure effects by adding redundant systems or managing systems responses to particular failures. Again, NASA did a lot of managerial things, but also a lot of maintenance things in the 1950s and 60s for their Apollo space program. So out of that came a whole range of new maintenance ideas. So they're able to identify and rank the severity of a particular mode of failure of an item within the system, and that's where this criticality came in. So basically it then became fail mode, effect, and criticality analysis. And again, as you go about looking at that, we can start defining really what we're talking about. So we talk about a failure mode, and that's the unexpected, contrary to design, behavior of a subsystem or item as a result of a physical defect or maloperation. So in other words, if you drive this thing too hard or jump up and down on it or drive it into the ground, well, again, that's a form of fail mode, isn't it? The effect is the consequence of a failure mode expressed in terms of the resulting unexpected behavior of the system. And the criticality is the product of the consequence of an effect and probability of its occurrence. The consequence multiplied by the probability. The steps in the process are, what you've got to do is list out the functions of the design, asset, or procedure under the investigation. Now for each function, identified list of all the possible failure modes that can occur. For each failure mode identified, describe the failure effect. Categorize the severity of the failure effect. Categorize the probability of the failure effect. Calculate the criticality of the failure effect. Again, based on that severity and probability, and rank the failure mode. So that's the overall process. And then the team carries this out, and then obviously all stakeholders should be represented, because it's no good if you're talking about something here and if you underestimate or overestimate because you haven't got all the information from all the parties, then again, that analysis is not going to be very effective. You need to hear from all people that are involved with the process, whether it's the installation or the driving of the vehicle, or whatever the case may be, or the operation of it. And then, of course, the maintenance people have to pick up the pieces. So really, keeping in mind that it's no good just the maintenance person getting the equipment and going, oh, okay, that blew up. The operator might be able to tell them things that might be going on. Okay. So the severity is characterized as high category 1, which is catastrophic. The failure may result in injury or death or environmental consequences. Oil leak, for argument's sake, so an environmental issue. Medium/category 2, which is critical, a failure which may cause severe injury, major property damage or major system damage that will result in major downtime or production loss. Low category 3, which is what's called marginal, a failure which may cause minor injury, minor property damage or minor system damage, which will result in delay or loss of system availability or degradation. Again, the other category, minor category 4, again minor, a failure not serious enough to cause injury, property damage or system damage, but will result in unscheduled maintenance or repair. All right, so the FMECA analysis is normally recorded as on a sheet, as per this example. So you can look at this worksheet. So you have functionality, the failure mode, the failure effect, the criticality, the probability of that occurring, what's our risk, and then obviously the prioritization comes out of that. Provide supply of seal oil, then the failure mode is that the main seal pump seizes. The failure effect is that the low level alarm sounds, auxiliary seal oil pump starts. Criticality of that is low, probability is medium, so again, what's my risk? So by going through and analyzing each of those particular items and then prioritizing them, obviously that helps you with regards to figuring out how you go about maintaining this particular device, and whether you pull it in to fix it, and then your scheduling of it, how often you do that. What's the relevance or application of maintenance of failure mode effect and criticality analysis? It's applied to assets to identify maintenance requirements. It's used to examine each critical failure mode to determine the best maintenance policies to reduce severity of each failure. Again, think about it. A severity of a failure is sort of marginal, low, high, and that type of thing. So the reality is that there are severity associated with that type of failure, because again, something could be easily fixed, so therefore then it's only a minor, as you saw, or it could be catastrophic, as we also saw. So that's interesting in itself. By examining that critical failure mode has a huge impact on your maintenance policy and obviously your maintenance planning and your strategy. Now, included in the reliability centered maintenance methodology, so failure mode effect and criticality analysis is in RCM. It's if sufficient statistical data of the kind that's been described as being collected on all the items of an engineering system, then it should be possible to estimate the expected reliability of a system as a whole. Unfortunately, both the length and complexity of such calculations increases exponentially with the number of items and the complexity of the interdependence. So yeah, so what they're saying is that things become complicated very, very quickly. So it just means that you might have to use some sort of computer program. And again, with maintenance programs, you'll find that some of these things have been computerized. So therefore, then you just put the data in, you're able to monitor it, and a number pops out the other end, or calculations done for you. We can talk about reliability block diagrams. So when designing complex engineering plants or engineering equipment, initially you draw a block diagram where each block represents one of the subsystems or items of equipment. You can have a schematic block diagram showing how the items are physically connected up. A functional block diagram showing the flows of power, material with inputs of outputs specified for each block. Later you go and then overlay on that, if like the piping and instrumentation diagrams. So you're building up the overall system, so therefore then you can look at critical elements, and also of course how things interrelate with each other. So you have an assessment of the overall system reliability when you do that, and that can be facilitated by constructing and analyzing a reliability block diagram. Connections symbolize ways systems functions as required and do not necessarily indicate actual physical connection. So it's a representation. Now, for ease of analysis, each item is usually modified or modeled, is modeled as either fully working or totally failed. So conservatively, partial failures are assumed to be total ones. So in other words, it's either a 0 or 1. It's either working or it's not. It's either successfully operating or it's a failure. If it's a blockage, it's, and it's working, but it's intermittent, well, it's still seen as a failure. So therefore, then these reliability block diagrams are constructed on the basis of functional, schematic, and/or piping and instrumentation diagrams. So it's collectively, again, the idea is that you're getting as much information as possible to enable you to help you understand what the problems are, what the failures might be, and how you go about avoiding them or having to, fix them up when they do occur. So this reliability block diagram, this looks at the example. This scenario is the system comprises a motor fed by 2 fuel pumps, both of which are normally working. If the motor is working, full power output will be achieved even if one of the pumps has failed, because as you can see, since they're in parallel, we're able to still have the output occurring. So the RBD, if you remember, RBD is the reliability block diagram, would still be appropriate whether the pumps were located in series rather than parallel, along a single fuel line or in parallel, provided that the full power would still be achieved even with one pump failed and that the feature would not block the fuel line. The reliability block diagram is determined by reliability. Logically, is this thing reliable? Not simply by the physical layout. So in other words, these things have to be able to operate so that overall, we don't really see a decline in the functionality of the overall process. All right, so let's look at this example. Consider the simple system. We've got 2 units. Okay, here they are in series. If successful system operation requires both units to be working, that is, if either one fails, the system fails. So if that one's not working, nothing's going to happen. If this one's not working, then nothing's going to happen. Then for reliability assessment, they are considered to be in series and are represented by, again, that reliability block diagram. So you can have this kind of functionality. You can have your parallel or inactive parallel. I'm going to look at a couple of these things as we cycle through now. So we look at series reliability. Failure probabilities of units assumed to be independent. That is, failure behavior of one is not influenced by the other. So, they're not integrally connected. So therefore, probability, mathematically, the expected system reliability at time t given by the product of the 2 estimated reliabilities comes from the mathematics. All right, so let's have a look at this example. We've got, again, as I say, if you look at the worked examples in the study guide, and what I do here, you'll see that I'll expand on them, show you some background information, give you general formulas, that type of stuff. So it's a good idea to go through these lecture slides and these lecture videos, or lecture slides at least. If you get access to those, you can see that I've expanded out on the explanations to help you. So in this case here, if the estimated unit reliabilities at t equals 10,000 operating hours are 0.90 and 0.95 respectively, then for this particular unit and for that particular unit, so it's 0.95 for that and 0.90 for that over a 10,000 operating period. Then the system reliability at that time will be, as we said, the product of those 2 things. So it's about 85.5%. It can be simply shown that if both types of unit exhibit negative exponential probability distribution functions, so again, it's not a normal distribution, it's not a binomial one, but we're saying that it's the negative exponential probability, then here's what the failure rate looks like for unit 1, and that's what it would look like for unit 2. So if we multiply those together, then as you can see, we need to think of our mathematics we did back in first year. We've got some indice laws to think about. So ultimately, that's what the form will be. Okay, and then when the time is relatively large, we can use this as, remember beforehand we had reliability was 1 minus the failure rate. So therefore then now we can, for a relatively large period, we're going to use this exponential form. So in that case, when we consider our unit 1 and unit 2, so therefore then this is unit 1 and this is unit 2. So again, for series reliability for a 2-unit system, it's just R1 times R2. So we end up with this general formula again. We know what lambda 1 is and lambda 2 is, we can do the calculation. So these are just general formulas. And then we can talk about the mean time to failure. So again, it's for a series, and remember we're talking about series reliability. So that's 1 over the lambda for the actual system. In this case here, it's made up of 2 units. So therefore it's 1 divided by lambda 1 plus lambda 2. All right, so that enables us, for a very simple system, this is the general formula for it, to go about analysing for each individual facet of particularly what will happen overall to the failure rate or the reliability. So let's put some numbers now. So for this example, we'll look something. We're going to look at mean time to failure for the first unit is 100 hours, and for unit 2, again, as we go through, it's going to be actually 200 hours. So therefore, then that's 1 over 200. So therefore, then 1 over 200 will give you 0.005 per hour. Now for the system series reliability, again, we just go back to the formula we saw beforehand. So we just got to multiply them through. So now I gave you those general formulas before, we rather derived them in that first example. So now we plug in numbers, and pretty much that'll enable us. Now whatever time it is, 10,000 hours, whatever the case may be, we can start putting in 100 hours, whatever the case may be. And then for the series reliability, it was of this particular mathematical form as we saw. So therefore then we can do a calculation. So for this particular series setup, with these particular mean times to failure, then of course we plug it in here. The series reliability for that is 22.31%, so 22, roughly 22%. So therefore then, once we do that calculation, again, we can use that to help us figure out, the scheduling of our particular maintenance. The system mean time to failure, again, was 1 over lambda s, which in this case there were 2 units, each of lambda 1, and then the other one had lambda 2. So again, what we're saying here is that the mean time to failure is about 67 hours for that 2-unit system. So again, that enables us to think about how we go about scheduling. We know more about the reliability of that system now. So it's not this ad hoc qualitative kind of, oh yeah, you should go and fix that at every, 100 hours. Well, hang on a minute, if you go and fix it for every 100 hours, you're going to have one. Sometimes you're going to be okay, and then other times we're saying here is that really the mean time or the average time is about 67 hours. So again, it helps us with the prediction for the failure, but also with the regards to the prediction or the scheduling and planning for our maintenance. So all that is required in the case of series reliability systems with more than 2 units is the simple extension of these calculations. So, if we do that, you can talk about availability calculations as well. So if we go here, we've got not 2 units, but we've got 4 units now. So as you might imagine, we're now going to talk about availability. So each example leads on and gives you some like a different focus. So this particular example, again, if you look at the study guide, you won't have this much detail, but that's why I tried to blow it out here to give you a bit better idea. So, and also they're introducing this idea of availability now. So what we can do is that a simple process flow system is occurring here. It's got 4 units that are running continuously like that. It's got no redundancy, that is the units are in series reliability, and the units are subject to randomly occurring failure and repair outages, which result in the average unit availabilities of 98, 98, 96, 95. So 98, 98, 96, 95% respectively. The system is available only when all units are working, because obviously if that drops out, nothing happens. If that one drops out, nothing happens. So they all have to be available. So for series reliability, if the failure of a part leads to the combination becoming inoperable, the 2 parts are considered to be operating in series. So let's look at this particular thing here as a little example. So if 2 parts, X and Y, are considered to be operating in series, if failure of either of the parts results in failure of the combination, then of course we can go about saying that the combined system is operational only if both part X and part Y are available. So we talk about AX and AY. Now from this it forms that the combined availability is a product of the availability of the 2 parts. So here this is just giving a little bit of introduction saying, hey listen, if we've got 2 things going on like we had above, then that would be the availability. But so it's just simply a multiplication of the availabilities of the individual units, X, unit Y. But here we've got 4 units, so that's just a little derivation. So here now we're saying we've got 4 units, so exactly the same thing. So it's going to be a product of 4 of those things. So we've already set up here, we've got, that's 98% availability for this particular one, 98% for unit 2, 96% for unit 3, 95% for unit 4. So when we take that into consideration, what it's telling us is that even though we've got numbers like 98, 98, 96, and 95, really what that's telling us that overall as a system, it's 88% reliable. So that gives us a good insight into how we go about designing our maintenance. If you've got availability, then you can also have a calculation for unavailability. So it's just simply 1 minus the availability. So therefore, 12% of the time, it's going to be unavailable. Okay. So we could do that calculation above, the calculation here, by either looking at the unavailabilities, and that's what I've done here. So if you calculate the unavailabilities, this was 98% available, so that's so it's 2% unavailable. Likewise, that was 98%. This was 96%, and that was 95%. So therefore, then that's the availabilities. So therefore, the unavailabilities is going to be 2%, 2%, 4%, 5%. So again, that roughly is about 13%. So if you do the calculation, it's 12, but that's a rough calculation. This comes from a guy called Lusser. And Lusser's law was named after the World War II German ballistic engineer who seems to have been able to be the first to express it formally, which is that the reliability of a series system will always be less than that of its least reliable component. Common sense in lots of ways, but mathematically it's been able to be shown to be true. Now, what about a parallel, an active parallel reliability? What happens in that particular system? So here we go. That's our active parallel. That's the configuration that we have. Might be 2 pumps for argument's sake. 2 units, active parallel reliability. The unit reliabilities being in the early series example. So if we take that 10,000 operating and we had values of 90 and 90 and 95 or 0.9, 0.95. The system active parallel reliability at 10,000 hours for these 2 units will then be this little formula. Again, as I say, I give you some stuff that's missing from the study guide. So when you calculate that, put all your values in. Therefore, then we'll end up with this, which is about 99.5% is going to be the reliability of that particular parallel system. All right, that's good. And then we can extend this, of course, beyond 2 units. And again, if we've got n units, then basically it's going to be this little formula. So that's, again, just some background information for you to extend it a little bit. Now, if with the 2 unit case, going back to that, both units operate in their useful life, negative exponential probability distribution, so that's particular, not a normal distribution, not a Poisson, not a binomial, but a negative exponential probability distribution function, then it can be shown that the system probability distribution function will not be a simple negative exponential. In fact, when we plug it in, we'll see that, look at it, it turns out to be this rather interesting function here. So again, if we know lambda 1, lambda 2, we can go about doing that calculation. So keep that in mind. But again, it looks highly complicated, but it's just really straightforward first-year mathematics. All right, and again, we can calculate for the active parallel reliability, the system's mean time to failure. Again, it looks like what we had beforehand, but now we're dealing with parallel, not series. So therefore, then it'll be 1 over lambda plus 1 over lambda 2 minus 1 over lambda 1 plus lambda 2. And these little formulas are, again, if you know what lambda 1 is, either that'll be given by the manufacturer, or you might have to calculate those things. All right, so here's a little example. So if we consider a system from the previous one that was that 100 hours and 200 hours, so therefore lambda 1 and lambda 2, if you remember, we were able to calculate those. Plug them in our formula. So again, the mean time to failure in actual fact will be 233 1/3 hours. So as before, the same parallel system logic applies to the availability characteristics. So again, these are the kind of calculations that we're able to do. What about this one? What happens if you have 3 particular units? In this case, we're talking about 3 chemical reactors. Again, they're in parallel, as you can see. The system is down only if all 3 are down. The reactors are subject to randomly occurring failure and repair outages, so that's the type of failure that we have, which result in an average availabilities of 60%, 70%, and 80%. In other words, the unavailabilities is that's 100 minus that, which is 40%, 100 minus that, which is 30%, and 100 minus that, which is 20%, or we write them as decimals, 0.4, 0.3, and 0.2. So again, for the parallel, we can go about, like we did with the series, we can find the unavailability and the availability. So in this case, For 3 units, that's going to be US equals U1, the unavailability of unit 1, unavailability of unit 2, multiply the unavailability of unit 3, multiply is going to get 2.4%. And likewise, we can find the active parallel reliability in terms of its availability. It's just 1 minus the unavailability, which is going to be, in other words, 97.6% of the time, this particular system here will operate without failure. Each of these examples illustrates, of course, the converse of Euler's law, in other words, the availability compared to the unavailability. So that, yeah, quite useful. We can have active parallel reliability with partial redundancy. So in some cases, the output from an active parallel system of several identical units may be deemed acceptable if at least some of the units are working. So such systems are termed partially redundant. So they're also called R out of N redundancy systems. So again, study guide doesn't talk about this, but I'll just give you some extra information. In this case, we have R units out of a total N units that are working. And in a general sense, for parallel and series networks, we set these values of R equals 1 or R equals N. So for parallel, R equals 1, and for series, R equals N. And you end up with this, as long as they're independent and identical units, you can use this little formula here. If you've got unidentical units, then that formula will change, but we're going to stick with identical units at the moment. All right, let's have a look at an example for active parallel reliability and partial redundancy. And what we have here is that an aircraft has 4 identical but completely independent engines. It will continue to fly safely if at least any 2 engines are working. Makes sense, doesn't it? Now, for each engine, the observed mean failure rate, given that it started successfully, of course, is equal to lambda equals 0.01 per hour. So the mean time to failure is 100 hours. Not sort of engine where you're in trust life and so in other words, 100 hours is not very long for a flight for an aircraft to be operating within. Now, given that the aircraft is taken off successfully, what's the probability that it will not fly safely for 10 hours, assuming that all failures other than engine failure are negligible? So other problems might occur, but they're not going to affect the overall engine viability. So the active parallel reliability with partial redundancy for each engine at T equals 10 hours will be this little formula. And again, that 10 hours is considered a long time. So we're going to use that little exponential formula for the reliability for the active parallel partial redundancy. So we can calculate that, plug in our numbers. We're going to get 0.905. Now, the system reliability for each engine at T hours will be, again, 1 minus the failure rate. So therefore, then to find the failure rate, we just rearrange the equation. So the failure rate must be 1 minus the reliability, system reliability. So therefore, we can calculate 1 minus 0.905, which gives us 0.095. Now moving on, what we then do is use that little formula. And as I say, the textbook doesn't give it to you. It just suddenly writes down the answer. But here, this is really how you go about doing it. So here, we're using that formula. Our time is 10 hours. We're using a parallel network, so R equals 1. So we're going to start from I equals 1 to N, as we see here. And then, of course, we've got 4 engines, and we've figured out that RS equals 0.905. So if we generate this little formula, now this is This is actually coming from the binomial probability distribution. So that's the general form for a binomial probability distribution, and we can multiply that out, and again we get 1, 2, 3, 4 terms. But the reality is we're only interested in this one because this is the one that talks about, representing all 4 engines failure. So if we do that calculation, you'll find that, so we just concentrate on that particular term. Do that calculation, we'll find that that will occur within 0.31%. All right, so again, as I say, modeling the behavior, picking up on a particular, again, this is using that binomial idea, binomial probability distribution. We're able to go about calculating system reliability for that particular, well, in this case, an aircraft with 4 engines. Now, you can also have inactive parallel or standby redundancy. So if we go back to that original diagram, we've looked at that one, the series, we looked at the active parallels, and now the standby one. We're going to concentrate on this one. is what it looks like. The analysis even of this particular arrangement can be complex. There are several different ways it could fail. Unit 1 and 2 could fail. You could, because it's standby, something standing by, so it can sit over there quietly to one side, and therefore then, you can then bring it online when required. So these are the different ways it can fail. So number 1 and 2 can fail, 2 pumps maybe. Failure of D to divert when required. D wrongly diverting to a failed unit. So in other words, as you're switching through, you're actually thinking you're switching over to the one that's operating, and of course the failure of D to transmit the flow, so nothing can occur. So they're the range of failures that can occur. Issues. Online units could fail while the parallel units might still be under or awaiting repair. Complex analysis is accomplished by this Markov discrete state chain analysis, and again, it's another mathematical technique. Or via computerized simulation, you can run little simulations on these kinds of things. To date, assumed the unit or the system can be in one of only 2 states, either it's working or it's failed. So therefore, often the case, some units and hence the system can operate in a partially reduced state. If the likelihood of this is significant, must be taken into account in reliability calculation, and obviously that's going to require more computations. Consequently, combining the analysis of these situations involves the assessment of the reliability of a system of many units, not just these. I mean, that's only part of a system, so what about everything else? Joined in a complex arrangement of processes, signal or energy paths, which obviously is a very lengthy job. So, however, there are ways of systemizing the task and computerizing them. So we're only looking at one small part. There can be, other units over here, for argument's sake. All right, and again, the Markov discrete analysis, state chain analysis. I'm not going to go into that, but it's just to highlight that there are, there's many approaches that you can use, statistical or using probability. We're looking at that inactive parallel or standby redundancy, and looking at the truth table, and just for large systems. So we've got this. Well, this is a large system. We're going to consider this little system here: pump X, pump Y, and pump Z, and it's got reliabilities of RT for the units at the same time of interest. Okay, so now as you might imagine, if success of operation is X, then 1 minus X is going to be the failure, because if you remember from probability, it's always 1 minus the particular value. So these are the failure expressions. And of course, what we can do is look at 1s and 0s. In other words, when 1 is a success, or means that it's operating, and a failure, it's not operating, then you've got a failure. So from, again, even this very simple configuration of pumps, for argument's sake, you can come up with a truth table. So when you generate the truth table, of course, you go through X, Y, and Z, pump X, pump Y, pump Z. It's on, it's on, it's on. It's X is on, Y is on, Z's off. And you just go through those combinations to figure out what's occurring. We're going to concentrate on just the first 3, because the status of the system, and again, this has been determined not from what information we've been given. So therefore, then we're only going to concentrate on those 3 and figure out the analysis from that. However, how they go about, just to highlight to you these little calculations of X, Y, and Z, and X, Y, 1 minus Z, to remind you that it's like a probability of failure of 1 minus P will give you the the probability of a failure. So that shows you. I'm just trying to show you where these combinations come from. So therefore, a failure is really 1 minus Z when doing the physical calculation. So that's where they come from. And then, of course, when you plug them in the little formula, you have picked up each of those. So there's 1, 2, 3. We're only concentrating on those 3. So there they are there. Multiply those out and simplify it, and of course you'll end up with this. And then we can do our calculation for the reliabilities for X, the reliability for unit Y, and etc. So we've got those combinations. This is the information. Again, they've just given it to us from some other analysis. They're the particular reliabilities for units X, Y, and Z, and we're talking about 20 hours. So again, you pick up this little formula, plug in your numbers, and we're talking about that the reliability is that 73% of the time this system is reliable, doesn't have any problems. So therefore, then again, if we can use that as the basis of a calculation, we can then figure out how we go about maintaining this particular 3 pumps And again, this could be part of one small part of the system, as we talked about beforehand. But that enables us. Now that we've got a percentage, we can now figure out that 73%. Does that mean when we're doing our calculations, ultimately should we be, and that's 73% over that 20 hours. So therefore, then that enables us to go about scheduling the maintenance and predicting when there might be a failure. So again, just concentrating on inactive parallel or standby redundancy, looking at that truth table. The method can be extended to take into account reduced output states, analysis of large or complex systems, basically have to computerize them, and with units of high reliability, problem can be alleviated by assuming possibility of more than, say, 3 or 4 simultaneous failures is effectively 0. So again, it just means that you can extend these kind of things beyond these simple examples of 2 or 3 things in parallel. All right, so let's have a look at this. This is again the analysis of large reliability block diagrams may be carried out in stages. At each one, small groups of units are analysed by the methods so far described, whether it's, as we said beforehand, putting things together in terms of its availability or unavailability, and then allowing the reliability block diagram to be redrawn in a reduced form. So while this all looks very complicated, basically what's happening here is that we got a complex or a large system, and we're able to take that and reduce it down into ultimately a single block. So the first part of the process is that we look at the things here in series, and we're able to look at those things. And look, they've got exactly the same value: 0.9 reliability, 0.8, 0.9, 0.8, 0.9, 0.8. So if we go through with that series connections, we can reduce it's number 2 and number 3, unit 4 and number 5, unit 6 and unit 7. If we do that, then each of those will be, we can multiply those together to get 0.2. So when we do that, over here you'll see that we've got unit 2 and 3. We can combine those down, and obviously its reliability is now equal to 0.7. If we take unit 4 and 5, we can see that that reliability now comes 0.72. Unit 6 and 7, we can reduce that down to a single block of 0.72. Then what we do is that we look at the blue ones. Again, they're all in series, so we do exactly the same thing. So we can have 8, 9, and 10, 11, 12, 13 doing exactly the same idea. So as we shift from reducing this complex looking system down to this, we can then continue with our analysis. So in stage 2, this is a parallel block, another parallel block, and as we saw beforehand, we've got to use our little formulas. So they differ for parallel and series, of course. But we just use the little formulas we've been talking about. So now we're saying we're going to call this group 2 to 7. So it's 2, 3, 4, 5, 6, 7. So 2 to 7, we can use our little formula for the parallel that we saw above, and we can calculate our probability for our availability. And likewise, we've got 8, 9, 10, 11, 12, 13. So 8 to 13, we can calculate our availability again using that formula. And then we just keep reducing. So on the next page, we're now going to concentrate on this one. They're in series, so we can reduce that down using our series formula. Then ultimately, these are down in parallel. So again, using our parallel formula, and we end up overall for a system that the system availability is 0.98%. Keeping in mind that that then comes down to 1 year block. So the idea is that you have these complex systems that you're able to analyze and take it down into something manageable, and then able to do an ultimate, in this case, systems availability for this complex system overall. Okay, so that's another method. Then moving on to the next method, which is the statistical process control, and this is a category of things. So again, the 1930s were a big time in industry. The Depression was on across the world, so people looked at doing things more efficiently, etc., etc. So that was part of it. Part of the growth in the manufacturing, Henry Ford and that type of stuff, with these kind of production line processes. So the 1930s saw a lot of this development of statistical analysis. The Shewart guy from Bell Technology Telephone Laboratories, he started developing this idea of statistical process control. In World War II, it became a significant problem because during the war, particularly in the Pacific, when equipment arrived, basically 50% of it didn't operate, so there was not great quality assurance. or quality control. And then after World War II, it kind of went out the window because there was such boom times in the American economy that they were more interested in maximising output and profit. So therefore, it sort of went out the window a little bit. Japan was occupied by America after the Second World War, so a lot of American influences came into Japan. When Japan was rebuilding after the Second World War, radios and cars had a really poor reputation for their poor quality manufacturing. But over time, pretty much investment was put into those companies, and Toyota, Suzuki, all those kind of companies became quite powerful because of some of these methods. In particular, around about the Vietnam War, the Japanese, again, like the Americans using these processes, the Japanese adopted and basically well, they certainly instigated them, but they also adapted them to their own processes. So adopted them and adapted them. So a classic example for statistical process control was the total quality control process that came out of Japan, as one example. All right, so what's its relevance to maintenance? Well, the main aim is about compiling data and statistics. So it provides information to guide efforts to improve product quality. The maintenance professional, well, in your case, it's going to be hopefully helping you to improve reliability, reduce job times, and tracing the cause of equipment damage. Identify maintenance opportunities and provide strategies to pinpoint problem sources and also maintenance scheduling. 3 tools must be used, most used to monitor it is the histogram, run charts, and control charts. All right. So the histogram, you get your data and plot it out like we saw before in that other example. You can do run charts, graphical tool used to monitor trends in certain conditions with time. Powerful analytical tool allowing you to display and analyze data. Clearly demonstrate what's happening in the situation being analyzed. Clearly compare one data period with another and to highlight what the changes might be. And the run chart or time chart, its axis is always time, so therefore then you can very, very clearly see and track a particular variable over time. How do you generate a run chart or a time chart? Well, step one is to identify the variable and to measure availability, unavailability. Collect the data over a sufficiently long period. Now, again, your confidence in results is going to be more trials you do or more data you have, and it could be just continually updated rather than being accumulated. You could have an online process that's continuously updating your data. You plot out the results and then you basically analyze the trend or trends. You examine the running record of a process variable over a time period. Okay, so inevitably some variation in the measured data. Analyze data in groups, say weekly periods, monthly periods, 6 monthly periods, quarterly, whatever might work for you. And you're able to calculate the mean, the quarterly mean, the monthly mean, the 6 monthly mean, whatever it might be. Now, as you accumulate data over time, you can identify patterns emerging and plot the mean, range, standard deviation, that type of stuff. So again, you're starting to analyze these statistically. This guy, Shuwat, and others, they highlight a process, basically economic limitations reducing to such variations. So you've got this tension all the time between identifying causes of the variation. So which are acceptable and which are not acceptable. So, from a statistical point of view, you can talk about common causes. They happen by chance and are common to all or most operators, machines, or processes. So it's inbuilt. It's common in the context that it's expected that that's going to happen. If you've got particular machinery, of course it always overheats, or that's the way. If I've got a conveyor belt, of course the bearing is going to run down. Of course, the actual conveyor belts themselves are going to wear down. So, common causes. And then special causes are traceable to a specific machine or a particular person or a particular local effect, such as the change in the quality of raw material. So these special cases, again, you have a conveyor belt, everything's going along, the bearings, of course, if you don't grease the bearings, they're going to seize up. So common cause. Or there's a lot of dust, so therefore, dust is going to get into the grease, into the rollers. affecting the relevance. Special cases might be that a particular item or the way a particular person operates a particular device, then if you take that person out, then of course you're going to find that hopefully another operator will not cause that effect, whatever it might be. People that say on haul trucks, a special case might be a particular person who's very heavy with the machinery and doesn't treat it well compared to someone else. So that would be a special case. Now, not all variations are bad, because statistically you can look at this information, and this US statistician Deming, he highlighted that any common variation that produces acceptable product quality is acceptable, but special variation is always unacceptable. In other words, if you just got a machine, of course things happen and it runs down, it breaks down, that's fine. But then if you have the way that a particular, so that's acceptable, that's fine. That's why failure has occurred or why there's problems occurring. But the special variation, if you have somebody that's very harsh on the equipment or doesn't look after it, well then that's what's called a special variation, so it's unacceptable. You have to do something about that. You have to either retrain that person or move that person out and put somebody else in. So good quality does not necessarily mean high quality. It means a predictable degree of uniformity and dependability at low cost for the quality suited to the market. That's what Deming says. So these common causes and special causes are things that you need to be looking for and need to be able to design out of the process, at least monitor them, and then be able to compensate for them, or as we say, particularly special causes as a person or a specific machine. If this machine always goes down, that pump will always go down, well, replace the pump. If it's a particular person, well, you might need to move that person on to another task. Control charts, how you go about extracting the information. Well, there's no control over what distribution you may find. In other words, just because you've collected this data, it may be a normal distribution, probability distribution that you're able to use, or it might be that negative exponential one, or binomial, or Poisson. So therefore then, you've got no control over the data. It just fits a model. Now, the shape of the data depends on the process we're investigating, and typical distribution may be uniform, normal, skewed, or random. So the uniform one's evenly distributed across a given range. Normal is distributed, you get a bell curve, and then skewed would be you get the bell curve just bunched, moves across. Random, you get this what's called modal or bimodal, and that particularly, again, this is what the key feature of these mathematical models are, is that if you get this bimodal thing or multimodal thing, then that's telling you that there are multiple causes of problems, of failures. So therefore then it helps you with your analysis. It's just not one thing. Again, the issue is you've got to figure out what are these causes overall. And as I say, some you'll know from previous experience, some you'll know because you've gone beyond your 10,000 hours, so therefore of course that's failed. So if you've got three causes, three multi-modal patterns, for argument's sake, then at least one of them you can remove from your situation. The other two may be caused because of that particular problem, but it may not be as well. But again, it's giving you information that you've been able to analyze to enable you to pinpoint what causes of these particular problems are, and then obviously to rectify them and fix them up. Now, whatever the pattern of the original data, if we sample data, mean values of samples have a normal distribution providing enough sample size. So in other words, pretty much if you keep collecting data, the mean values of things typically follow a normal distribution, a normal probability distribution, that bell-shaped curve for the mean values. The small correction required to this theory if samples are small, but generally works well. So in other words, it works well for small things, like small systems. But when it gets larger, then you have to fiddle with it. And again, there are techniques and mathematical techniques and computer programs that help with that type of thing. This just talks about when you plot out the graph, you're able to find the mean and the range, etc., and you're able to draw them on your graph. So don't worry too much about that. And again, this is just some data. It just gives you an idea of what the data would look like when you do those kind of calculations. Don't lose too much sleep over that. It's a process. It really is useful, and it's just another technique that falls in this what's called a category of statistical process control. Yeah, same with that stuff there. But the analysis is important. So as long as process is only subject to common variations, as we talked about, you know, typical things that would happen with the machine, obviously it overheats, or you know, the failure has occurred because that belt broke on it all the time. That's good. That's common. That's fine. It's expected in that context. When it occurs, may not be expected, but it's these special cases that, as we saw, special causes that are things that you really need to pinpoint because they become quite random, possibly. In the context that you might get a random error, but the reality is that it's not random, because as long as you can pinpoint that it's an operator that is causing special situation to develop, then obviously you can change things around, like we talked about before. Other effects that may be produced by special causes are runs when 8 or more consecutive points lie on the same line. Okay. So this is just some terminology related to the actual plot, but don't be too concerned about that. And as we move just closer to looking at the last type of statistical process control, the Pareto analysis, developed by Pareto, again, lived in died in the early 20th century. So again, getting on to that 1930s. So a lot of mathematical, statistical stuff happening around that 1930s area. Relatively few items account for a majority of any given result. So in other words, you know, it's only one small thing that has to go wrong for the majority of things to, in the majority of situations that we have. Graphical representation for identifying the highest priority opportunities from a number of alternatives, and particular items, assets, or events that may consume more resources, labor, material, uptime, money than others. Means of ranking these opportunities. So that's what the analysis is about. So here we go. Let's look at an example to help us sort of figure out a little bit more what this is about. An offshore oil and gas extraction system consists of several identical platforms. Each platform comprises 100 different subsystems. For some years, records have been kept of the maintenance man-hours expended on these subsystems. A Pareto analysis of these records is required. The first step is to calculate the total work hours for each subsystem type, and that's what this table 5959 is doing, and which the subsystems are ranked in order of man-hours expended and is then produced. So, okay, you've got all these systems, your lighting system, gas production, your gas well, electrical generation, compressed air separation. So, okay, and then you go through, you figure out your man-hours, and so that's, and you can calculate them as a percentage as well. And then you can, a bit like we did beforehand with that histogram, you can also do a collective, a cumulative percentage, because then you can read off values at a particular time. And that's, again, this is generating data like you might get from a manufacturer, but of course, that doesn't occur here. You're able to generate your own data, and from that, you can start doing some analysis. So you can do a histogram like we talked about, and again, you can get an idea of what's occurring at particular times, just visually by looking at it, and of course then reading off specific references and what's happening. The cumulative plot, as I said, with that data, that's looking at column 5, you can do that, and again, you can say things like, oh, okay, at this particular percentage of the systems, what's happening? Well, that's the number of work hours, or vice versa. You can say something like, oh, at 60 work hours, then the percentage of my systems that are going to be failing might be around about 15%, something like that. So again, it's data that you've collected, data that you can interpret, nice graphical representations that you can very quickly look at and basically, do a snap decision. I mean, looking at that table of data and trying to make a decision quickly to do something may not, We are far better looking and analysing visual things. So straight away, if something was happening, you can say, okay, right then, oh goodness, we're up to 50% of our work hours. What's the expectation? Yeah, again. So visually, it gives us a better idea. Snapshots. The cause and effect diagrams. This is the last particular method that we're going to look at. Again, there's many others, maintenance methods as well, but this is just a snapshot in Module 4 and Module 5 with some of the different types of maintenance processes, strategies, theories that you can come across. So cause and effect diagrams, They are a tool for organizing causal factors leading to a problem. It's a graphical representation of the problem and the causes of that problem, developed by this Japanese gentleman, and they sometimes call it a fishbone diagram. So what you start doing is looking at the different characteristics of your people, your staff, the materials that you have, the machines, the measurements that you are, using, whether it's online condition monitoring, the environment, how dusty it is, it's a hot environment, and the methodology that's being used. As you can see, it could be the lack of operating instructions, so therefore an operator hasn't been properly trained to use this particular device or machinery. So what you're able to do then is go about with your analysis. The best results in a cause and effect analysis are gained by gathering all the people involved in the problem and its solution together. Because again, if you're talking about people, materials, machines, etc., well, if you can get insights from as many players as you can, then you're going to get a better idea of the types of things that are occurring within each of these, causing, and what the effect will be. Carry out a brainstorming exercise to list all the possible causes, collate them into subgroups, and then draw the diagram, as you can see. And when the exact relationship between the cause and effect can be proven by data, a box is drawn around that cause. So let's go down. You can start saying things like, here's my creating it. I can go back up there. First of all, so as you're going through here, you might say, oh, okay, problem statement. So out of that, you can start saying, oh, hang on a minute, it's because of this lack of operating instruction. For argument's sake, is the prioritization that you might do, or it could be from dust. So therefore, then you would put that down as your ultimate cause for this particular problem. So how do you go about mitigating that? It may mean dust suppression of some sort, but the reality is that you've got all these things occurring, so you can start pinpointing them, and then by highlighting dust, for argument's sake, then you are able to communicate that effectively to the team to go about trying to solve the problem and rectify it. And then finally, I just follow through this little example here, following through these steps, creating a cause and effect diagram. So first of all, identify the problem. Again, remember you're brainstorming with people, get as many people as you can in the room with regards to why the problem, what the cause of the problem is and why it's occurring. So identify the problem or the issue to be modeled from the diagram. The pump is tripping on the high oil temperature or late monthly maintenance cost reports, whatever it might be. Identify the major cause categories, and we talked about those above. That's people, methods, procedures, systems, policies, environment, skills. So that may not work for you, but in your organization, you might have external maintenance contractors, for argument's sake, or you might have suppliers that don't deliver on time. So whatever your list of things might be, they list them out. So identify the major cause categories that will exist off the cause effect fishbone diagram. Good place to start in determining. So as I say, some examples that way. So here, this one here is talking about the accounts department, the procedures, computer system policies, late monthly cost report. So just as an example. And then step 3, having identified the categories, accounts department, procedures, computer system policies, reduced timely maintenance cost report for this particular problem, then apply a group technique to detail any possible causes under these categories. So here, the accounts department says that communication, new procedure with report requirements, communicate new procedure with report requirements, determine report time requirements, rewrite the policy. And therefore then, as you can see, brainstorming, as we can see, generate that. And then number 4, look for the most likely cause of, or causes. Good start to circle or highlight probable causes that appear in several of the major categories. For example, maybe it's not enough people, maybe it's runtime, that's payroll, date unrealistic, whatever it might be. In the process of questioning each cause listed, test questions like, why is this a cause? Is this a cause? Just because it's been suggested, it may not be a cause, it may be a suggestion, but then ultimately through your analysis discussion with your group, it may not be a cause at all, or it's a symptom. The end result of your process is to list the most likely causes and agree on what they might be. And therefore, obviously, you can target them, test them out, try and rectify them, and then again, hopefully, overall the problem will go away or be reduced. Now, using some tool, a matrix diagram, assign responsibility to resolve problems. So now, these are the actions arising. So, once you figure out what the cause is, so if it's not enough people, well, that may not be a cause, it might be a symptom. So therefore, then you have to deal with the symptom. If you're able to increase the number of people working in that area, well, then that symptom goes away and you go, all right, fair enough, I've solved that. Therefore, you're able to rectify that. Cause and effect diagrams used to describe a defined problem situation. This could evolve from the chart used to identify the possible causes, probable causes. Eliminating inputs that are not causes and changing the causes into resolution statements, solutions can be formulated. So really, basically what it's saying is that generate this diagram, start with the particular categories, start looking at brainstorming about different things that can occur to rectify whatever the problem is, and then prioritize or basically critically analyze to see, what is the critical cause of the problem. Because even though you have this range of things, the reality might be, it might just be the little communication, for argument's sake. And communication can take various forms, or it could be the actual procedure and the processes that are going on. So yeah, you can have all the communication in the world, okay, but the point of the matter is that the procedure's too long or too convoluted or it's not detailed enough, then nothing's going to happen. You can basically talk all day about it. Even though you've got good communication channels, the reality might be that you have to change the procedure. So ultimately, you draw a box around that, for argument's sake, and say, well, no, okay, we've got to rewrite the procedure. So then you do that. That's not the end of the problem. You go about rewriting the procedure, and then obviously you come back through again and see if the problem is still occurring. And maybe it's not just that. Maybe it's got to do with other things. Maybe you have to, look at the manner in which the operator has been trained, for argument's sake, or that type of thing. So whatever it might be. Maybe the computer system's out of date. Maybe you have to update a particular computer program that's with your maintenance schedule. All right. Essentially, though, what it is that Module 5 is looking at some other maintenance management techniques. As I say, it's not the end-all, be-all. It's just some more. There are many others. It's just a snapshot of some of the typical or some maintenance management techniques that you can use. You can draw on others. You can use those appropriately as well. And hopefully that'll give you some insights overall.